Hi and welcome to this lecture in which we will talk about waves. You might think waves is a rather general topic, but keep in mind that wave phenomena can be found in almost everywhere. For example, waves can be a feature of a certain domain we want to sense. Or an instrument might use waves in some form to measure an object. Or even both. But what is a wave? Well, that's not so easy to describe. If we look it up on Wikipedia, we get sort of a fuzzy definition. It says, in physics, a wave is an oscillation accompanied by a transfer of energy that travels through space or mass. I would like to highlight the term oscillation. In its original meaning, an oscillation is a repeating variation between two or more different values. And in most cases, these variations happen as time passes. Let's have a look at this graph. Here a certain value or property jumps between two discrete values. For example, someone switching on a light, turning it off, switching it on, etc. is generating a kind of oscillation. Okay, but that's not very impressive, right? Let's look at this oscillation. Now, there are no longer two distinct values, but rather an infinite number of states which are reached periodically. In general, oscillations can look very different. Here are two examples. On the left, we have a so-called damped oscillation, where the range of values that are reached gets smaller over time. On the right, we see something similar, except that the range of values gets larger and then smaller. Again, there is an infinite number of ways what an oscillation can look like. The most important feature just needs to be that there is some kind of repeating pattern. Now these are examples of oscillations. But are they waves? If we recall the Wikipedia definition, there's more to it. We need to fulfill a second important condition, which is the transfer or transport of energy. But how can an oscillation transport energy? Let's take an example related to our planet. Earthquakes. There is a certain type of oscillation that shakes the ground with up-down variation. At the location of the earthquake, the ground is moved up or down distinctively. This disturbance moves outward from the location of the earthquake. Now the interesting thing is that the ground only moves up and down and energy is transported by such a phenomenon. Actually, the fact that energy is transferred from the location of the original earthquake event is what makes them potentially harmful. So now we have an example that meets both main conditions for a wave: repeating variations or oscillations and the transfer of energy. Wave phenomena can occur in all kinds of environments, in water, in air, or in solid matter, as we have seen in our earthquake example. Waves might even propagate in vacuum, as electromagnetic waves can transport energy. There are four important properties. First, we have amplitude. Think of the amplitude as the maximum distance between the largest or smallest value of an oscillation from the mean over all values. The smaller the amplitude, the less energy is transported with the wave, which is kind of intuitive. Then we have wavelength and frequency. These two are strongly related to each other. Wavelength is defined as the distance from a point of a particular height on the wave to the next point on the wave where it's the same height. Think of it as the peak-to-peak distance, if you like. It is closely related to the term period, which refers to time rather than spatial distance. Frequency is given by how many of these maxima and minima are occurring within a certain time interval. This means frequency is reciprocal to wavelength. The shorter wavelengths, the higher the frequency, or the longer the wavelengths, the lower frequency. In general, frequency is defined as the ratio between the speed of a wave and its wavelength. This is a very useful relation, in particular when it comes to electromagnetic waves which propagate at the speed of light. As speed of light is a constant, we can easily determine the frequency if we know the wavelengths, and vice versa. The fourth important property of a wave is its phase. It describes the part of a wave cycle that has elapsed relative to an origin. In many cases, the origin is kind of arbitrary as the pattern repeats after a certain period. This means also that the phase can only give a value within a wavelength and never describes an absolute value. Okay, we have discussed the main feature of waves. There is one more thing that's really important to understand, and that's called spectrum. In many cases, when we study wave phenomena, it turns out the waves are composed of several basic wave components. If we plot the amplitude of these basic waves against the different frequencies they have, we get a so-called spectrum. Sometimes it is more convenient to plot the spectrum as a function of wavelengths rather than frequency. In particular, when we deal with quantities which we're very familiar with, like light that is visible for the naked eye. Here's the spectra of 4 different light sources where we plot the wave amplitude of the light waves as a function of wavelength. Bluish light has higher frequency but shorter wavelength, so we find it at the left side of each spectrum. Red light, on the other hand, has longer wavelength and therefore shows up on the right edge of each plot. In the upper left plot, we see that daylight contains almost equally waves from different frequencies or wavelengths in the visible range. If we compare to a traditional light bulb, as shown in the upper right plot, we see that it's dominated by waves with longer wavelength. In other words, light bulbs usually give quite reddish light, the impression of a warm light, as you might have noticed. The spectrum of a neon tube is all different. It has distinct wavelengths or frequencies which are dominating the visual spectrum. This is attributed to the physical effects that generate light in a neon tube. And as the name already suggests, neon, which means the bluish part of the spectrum, is very dominant. Modern LEDs are a great invention, not only because they save a lot of energy, but also when looking at the spectrum they appear to have a nice composition of almost all colors or wavelength. Okay, in this lecture we attempted to define what waves are, discuss their properties and also introduce the term spectrum. I hope you enjoyed this lecture and I'm looking forward to see you next time.